Right, it's 12 o'clock. Let's kick off this webinar about testing services within the OWI-Lab consortium. Hello, everybody. Good morning, good afternoon, and good evening to some of the participants as well to this webinar. It's an international audience today. So welcome. I will quickly introduce who we are, what we are doing, and then let's kick in with the topic of the day, which is testing. Very quickly, OWI-Lab, it's a Belgian knowledge center, research and expertise consortium set up in 2010 with support of the Flemish government. It's currently led by CIRIS, the University of Ghent and the University of Brussels, in which we collaborate with the mission to support industrial R&D and innovation projects, actually, within the onshore and the offshore wind energy value chain. Our main goal is to facilitate fundamental but also applied R&D. And with respect to that, the three partners have set up unique testing facilities over the years, which also dedicated services, testing services have been set up or are being set up, which we want to share today with you. We are already doing this for 10 years, so there's also some experience, which we will also share today in the 4 individual presentations and by the experts. And so the talk of today is the supporting services, as I said, with respect to testing and demonstration. There's also other activities within this consortium. There's a broad R&D project portfolio. This will probably be something for the upcoming webinars, where we will deep dive into some of the projects and share some insights. The third action is indeed sharing these insights, sharing innovation and inspiration to the industry. And later on, at the end of this session, I will also give you an insight in what is coming up next, as we are organizing a wind energy summit in June with 3 specific actions. So the talk of the day is testing and testing facilities, and I will give the word in a minute to Professor Peter Trok from the University of Ghent, who will focus on a wave tank testing facility. Maybe first, some rules. Please be muted during the sessions. You can already post questions in the chat box, so we can already have a look at those. And then after each presentation, there's approximately 3 to 5 minutes for Q&A. So Peter, I'll give the first word and then give the floor to you.
Thank you very much, Peter Jan. I assume you all see the start slide of my presentation. My name is Peter Trog indeed, and I'm department chair of the Department of Civil Engineering, and I'm very pleased to be able to present to you today our new wave tank, which is available for testing. And obviously, I would like to present a specific focus on the offshore wind sector today. Here is an overview of my short presentation. First, obviously, I would like to quickly introduce our new wave tank, which we call the Coastal and Ocean Basin, or the COB, which is located in Belgium. And then I would like to take the opportunity to show you a short video, a brand new video, so it's some kind of a premiere, the launch of our new COB video. It's much more efficient in presenting the basic characteristics than I could do. And then as a third step in my presentation, obviously, again, I will highlight some very interesting topics related to the offshore wind developments. Here is still an artist impression, I would say, of the building in which our wave tank is located. The complete building is called the Flanders Maritime Laboratory, and it is actually composed of 3 individual modules. In front, you have the office module, and then the module with the yellow lines, that is the laboratory hall of our wave tank. And then, in fact, the largest module is in the back. It's the new towing tank, of Flanders Maritime Laboratory. Our COB will be operated not only by Ghent University, but by an excellent consortium made of two academic partners, Ghent University and KU Leuven, and Flanders Hydraulics Research, the governmental research laboratory. And jointly, we will operate the coastal and ocean basin. You saw an artist impression, and now you can see a photo of the actual status. And as you can see, I would say the COB is no longer under construction, but we are still finalizing the systems on top of the concrete structure, which you can see. We are installing wave makers, we are installing pumps, with the idea to be fully operational next year. If you do not really know what a wave tank is, then this slide could be interesting for you. Basically, a wave tank is nothing more than a wave basin in which we put a scale model of a coastal structure or an offshore structure at a particular scale, and we subject it to wave and current loadings. Also, wind loading is included in our case. And those loading conditions are generated artificially, but once they exist, the scale model is responding to the loading. And if you do it the right way, if you follow the right engineering laws, the response of the model is very representative for the real prototype. And just a few quick examples. This is an example of a floating wind turbine, which is tested in a wave tank under waves and wind loading. And another typical example is a scale model of a rubble-mount breakwater, where you can see that the armor layer stability is being tested under oblique wave action. So our wave tank is widely applicable, I would say, to a very wide range of client profiles, and actually also for a wide range of different project stages, going from early concept checks during the further development of a project. We can do your design validation as a complete design, or we can test details of a particular design. And even during installation or during the operational phase, it's perfectly possible to do tests in our COB for your structure. In terms of environmental loading conditions, I would say we focus obviously in a wave tank on waves, currents, strong winds, maybe also a little bit of flooding cases as the main focus. Okay, I would say we are ready for the movie. I think we are ready also with the sound. Here is a very quick overview of our new coastal and ocean basin. Please enjoy the next 5 minutes.
Welcome to the Coastal and Ocean Basin, or COB, in the Flanders Maritime Laboratory in Ostend, Belgium. The COB is operated by a consortium composed of Ghent University, KU Leuven, and Flanders Hydraulics Research. The COB is a wave tank with unique features which we'll present to you. The wave tank is used to test a wide range of scale models, ranging from coastal and offshore structures to marine renewable energy devices, under the combined loading of waves, water currents, and wind. The COB welcomes users from academia, industry, and governmental institutions, with the opportunity to develop innovative designs for coastal protection, offshore structures, and offshore energy devices. As part of the Flanders Maritime Laboratory, the COB is strategically located in Ostend Science Park in Belgium. It's close to a range of stakeholders who are very active in the blue economy and to other testing facilities such as the Blue Accelerator platform just outside the harbour of Ostend in the North Sea. The COB is a state-of-the-art wave tank composed of a 30 by 30 metre concrete structure with water depths between 0.3 and 1.4 metres. A 3.1 metre deep central pit enables testing of mooring lines in deeper water conditions. High-quality wave fields with a maximum wave height of up to 0.55 meters are generated using a state-of-the-art wave generator along two sides of the tank. In addition to the wave generator, a current generator is installed, generating currents of up to 0.4 meters per second. The currents can be superimposed on the waves, generating wave-current interaction in any relative angle. This unique feature will allow for better and more efficient designs of the tested structures. The state-of-the-art wave generator is positioned along two sides of the wave tank. It's composed of piston-type individual wave panels, and it generates highly accurate wave fields for regular and irregular wave conditions, including the option to increase the accuracy with second-order wave generation functionality. The wave generation system is also equipped with active wave absorption to minimize the amount of reflected waves in the COB. To correctly model the impact of the strong tidal currents along our coastlines on the scale models, the COB has a current generation system. The current is generated using propellers in the current tank, which is located under the wave tank floor. The propeller-generated flow in the current tank is smoothly introduced into the wave tank via grids in the floor. The grids are designed to achieve an excellent quality velocity profile. The current is generated in two main directions and interacts with the generated waves in any relative angle. The COB and its testing services are designed to facilitate the needs of the coastal and offshore engineering community for a very wide field of applications. Scale models of coastal structures such as dikes, breakwaters and harbours are tested to study wave structure interaction, armour layer stability, wave overtopping and wave transmission. In the COB, tests are conducted on large and more traditional offshore structures such as oil rigs, but also on innovative designs of floating structures with hybrid marine energy conversion technologies in both extreme and operational wave conditions before they are built. New coastal defence designs, involving nature-based solutions in combination with more traditional structures to tackle sea level rise effects, are challenging. The COB is offering new opportunities to test these nature-based solutions. Harvesting ocean energy using wind and wave farms is a challenging task. Design of the energy conversion systems such as offshore wind turbine foundations and wave energy conversion devices are carried out in the COB. And finally, the COB is a perfect testing environment for less obvious applications in the fields of wave interaction with floating structures for the offshore fish farming industry, mooring applications for floating wind turbine applications, or pre-operational studies of ocean observation equipment. The first projects in the COB will be exciting and pioneering industrial and academic projects. First, commercial 3D breakwater tests in the COB are conducted for the two large dredging companies in Belgium. The COB consortium partners, Ghent University and KU Leuven, are investigating wave energy farms and extreme waves in their international research projects. European projects can access the COB for their activities. Further, Flanders Hydraulics Research will carry out studies to support the governmental policy on coastal defence. The COB consortium invests in knowledge sharing with its partners. Regular seminars with the industrial, academic and governmental sectors are key to the COB's success. From the very beginning, the COB was supported by the key players in the Belgian coastal and offshore engineering sector, as well as the marine energy sector, who endorse a high-level wave tank facility. On behalf of the COB consortium, we welcome you to discuss your project ideas or to show you the COB and its testing services. Contact us directly or find out more about the COB on our website, cob.ugent.be.
I couldn't have presented it any better, obviously. But that was a rather generic introduction of the basic features of our new wave tank. In terms of the offshore wind industry, we can emphasize that our unique capabilities are the following. Our water depth is up to 1.4 meters, which means that we are neither a shallow water nor a deep water facility. So we are somewhere in between, which makes us mid-size and giving a balance between cost on the one hand and accuracy on the other hand. So in that aspect, we think we can fit a very good interest from your side. Both our wave and current fields will be generated to the highest accuracies available as state-of-the-art, and we will be able to include any relative direction between waves and currents. I would say also there we are one step further compared to existing infrastructure. It was only mentioned very quickly. In the center of our wave tank floor, we have a central pit of 3 meters diameter and 3 meters depth, in addition to the available water depth. So that makes it a perfect situation to test all kinds of mooring applications. And then last but not least, it's not only the wave tank and the wave and current systems which are important, also the instrumentation is key. And we were able to acquire a state-of-the-art motion tracking system, as you call it, from Qualisys, where we can purchase, as we speak, 3 camera systems, one above water, a second one underwater to fit the complete range of spaces, and also a mobile system for a specific focus. And with this Qualisys motion tracking system, we will be able to measure the displacements in 6 degrees of freedom of one body or even multiple bodies at the same time, making this instrumentation also very interesting for new developments. So that was a quick introduction of our new coastal and ocean basin. It's almost ready, and I would like to invite you, once we are operational, to discuss your interests. Thank you very much for your attention, and I guess I give the word back to Pieter-Jan.
Thanks, Peter. I think there is room for one question, maybe, if there is. If not, we will continue with the presentation of Christophe de Wispelaere. Is there a question from the audience? No? Okay, maybe later on. Let's then go into the second presentation, which is focusing on large-scale structural testing. Go ahead, Christophe.
Thank you, Pieter-Jan. So good afternoon, everyone. My name is Christophe de Wispelaere, and together with my colleague Koen van Minnebrugge, I am responsible for the large-scale structural testing within OWI-Lab. And we are from the Ghent University team associated to OWI-Lab. So what do we mean with the structural testing, or what do we focus on? Well, we focus on coupled damage mechanisms, and that covers the range from abrasion, erosion, corrosion to fatigue, fracture, friction and wear, and of course the potential coupling between all those. So if we think of an offshore wind construction, typically some of these damage mechanisms occur at various parts of the structure. So there's the well-known leading edge erosion problem. Within the turbine, there are various tribological contacts. So their phenomena related to lubrication, friction, and wear are important. And then if we think about, for example, the monopile or jacket structure, fatigue and corrosion are very important aspects. So in our testing, we focus on either the design phase and or O&M phase, so root cause analysis. So what we do is component design, material characterization, and testing. And I should also mention here that while we do have a large expertise in offshore wind, of course, the testing infrastructure that I will present today is not only applicable to that area, but to various other offshore constructions, or for example, dredging industry or other types of offshore energy. So what are now the testing regimes that we cover? Well, typically in a lab environment, you would like to test specimens or coupons, but what we really focus on is the testing of components and structures. What we mean with that is going to that I will cover in a minute. but particular focus is also on mimicking as closely as possible the environmental conditions. So Peter also mentioned this, and this figure already passed by a couple of minutes ago. So conditions related to seawater or the motion of the sea, temperature, realistic mechanical loadings. And so we really try to mimic this as closely as possible. Now, this is a picture of our testing hall at Ghent University in Zwijnaarden, and it already gives you an idea of some of the equipment that we have, of the scale. And so you see that it's not only small lab scale equipment for small lab scale samples, but really substantially large parts, components, and structures that can be tested. Now here on this slide, this video, I will let it play in the background. It gives you just a brief impression also of the scales that we cover in terms of components and structures, and also the scale of some of our infrastructure. Now, if you would like to consult these videos after the webinar, that's the reason why I posted the link here also on the slide. But what is important to mention here is what now are these large scale or the scales that we cover. So for tribological contacts, we go from centimeter scale up to roughly 0.5 meter, with loads up to a couple of meganewton. For fatigue, we cover the range from simple beams up to parts of bridges, and so quite substantially large parts, also up to 2 meganewton loads. And for static loadings, we can go from up to something the size of a beer bottle up to steel jackets or parts of steel jackets, and loads of up to 8 meganewton. So that is what we cover in this component and structure scale. Now let's first. So the first part that I will cover is on welded structures. So then we're typically talking, for example, about a jacket structure. Now, what an important test that we can do here is fatigue testing in a corrosive environment. Primarily, we do this on a component scale, and here, bottom left, you see a figure of our setup there. So a fatigue test surrounded by a chamber in which we can perfectly control the corrosive environment. So that's, again, this link with environmental conditions. And we can also upscale this type of fatigue testing to larger structures. What we typically get from this is SN curves for fatigue, and we also study crack propagation. Also important to mention is that we not only have the experimental infrastructure to do this, but we can also couple this with a set of numerical tools based on finite elements that has been developed in-house. Now, next, I will focus on the tribological contacts. And for tribological contacts, so then we're thinking about bearings. Bearings can be important, for example, to test in view of mooring lines, but also for the pitch of turbine blades. And in this test, so you see here on the right a picture and also a video of our large-scale radial bearing test rig. It is actually quite substantial in size, and for example, in this setup, we can simulate the oscillating motion of the sea and the effect it has on a certain bearing. And what we measure then is, of course, friction, wear rates, and potential failure of a bearing. Also here, the link with numerical simulations can be made, in this case based on computational fluid dynamics and fluid structure interactions. And so we can look at lubrication films, pressure profiles, etc. Then a third piece of infrastructure that I would like to highlight today is our shackle chain wear test rig, in which we, in view again of, for example, mooring line applications, for example, for floating wind, we can really test chains, typically 2 centimeters in diameter and 10 centimeters long. And very importantly, again, here we can test this in various media. So it can be water, can be sand, can be a slurry. And there we measure abrasion, wear, and wear rates, and again, potential failure. And we we can also make the link with all kind of phenomena that have an impact on the microstructure of the metal that has been used. So, for example, the material design, the production technique, etc. And then finally, the last piece of infrastructure that I want to highlight today is a very recent addition to our lab, and it is an erosion tester, primarily designed as a slurry erosion tester, but it has been designed to be able to adapt it for droplet erosion, and that is, of course, something that is relevant for studying leading edge erosion. So you see some of the specs here listed. It is, what you see here are still the renders of the machine that eventually has been built, and very recently it started operation as well. So let me end with coming back to my first slide. So within the large-scale structural testing at OWI-Lab, we focus on coupled damage mechanisms. Within the offshore wind context, you see most of these damage mechanisms occurring at various parts of the construction, and I also showed you that with the four parts of infrastructure that I highlighted here today, that we can cover actually a large range of these damage mechanisms within an offshore wind context. So thank you, and I now give the word back to Pieter-Jan.
Thank you, Christophe. No questions in the chat so far, but maybe in the audience there is maybe a question related to structural testing at large scale in the lab. If not, then we can continue with the next presentation, which will focus not on the laboratory testing, but the in-field testing of large structures. And I don't see any question popping up yet, so I'll give the floor to Christophe de Vriend.
Okay. Can you hear me?
Yes.
I see the presentation. Okay. So indeed, thank you, Pieter-Jan, for this introduction. In this last presentation, we indeed move from the lab to the in-field, to the real conditions at site. So my name is Christophe de Vriend. I'm a professor at the Vrije Universiteit Brussels, and already for 10 years involved in OWI-Lab, and with one of those main pillars of learning from the field. So testing of large structures, the large structures we are tackling in our research and in our services, or as you can see here, ranging from the large offshore foundations, monopiles, jacket structures, transition pieces, up to, of course, the offshore wind turbine itself, but also the installation vessels, such as the jacket vessels, and the offshore substation and all its large components on it. What are the testing conditions at site or in the field? Well, as it's written here, offshore structures, as we know, are really one of the most dynamically excited structures in the world. On one hand, they are subjected to the environmental loads, such as the winds, the waves, and the earthquakes. And on the other hand, you also have, of course, the induced loads and vibrations coming from the equipment and components installed on these structures, such as the rotors, the engines, or the switching gear on an offshore substation. So that's what you will find when you go into the field. What is the motivation of learning and testing or monitoring in the field? It's a bit the same, of course, as in the lab, but let's present here the three pillars. I think we are doing today in-field testing in the design phase for design validation, design optimization, or also certification of, for example, new foundation concepts. In the O&M phase, we're using data to gain operational insights, do O&M optimization, or root cause analysis in case of failures. And the last aspect, which is actually getting more and more attention lately, is collecting data to really understand what are the real loads at the site and how lifetime of these structures is consumed to be able to one day to make a decision on the remaining useful lifetime. So what is the type of measurements we do for these several aspects, and what is our approach? Well, over the last years, we have developed short-term measurement systems and long-term measurement systems. When we talk about short-term measurement systems, it's when you're going to perform measurements that last between 1 day and to 2 weeks. They're using these small mobile measurement systems, mainly consisting out of accelerometers. And long-term measurements, then a measurement system will be installed for 2 weeks or up to several years. And they are often focusing on loads using strain gauges. So I already mentioned some of the typical sensors that are used in our monitoring approaches and testing approaches. It's accelerometers, strain gauges, displacement sensors. But for measuring environmental parameters, also other sensors might be added, such as a wave radar for wave heights and wave directions, or environmental sensors linked to the water quality and the corrosion system. So I will, out of these 10 years of in-field testing, I will give you a quick overview of some kind of data that has been evaluated over the years. We've been focusing in the beginning mainly on the evaluation of in-field frequencies of offshore structures by collecting vibration data and using state-of-the-art operation model analysis. This has been done to, for example, compare as-designed frequencies with as-built frequencies. This has been done to evaluate the effect of a scour protection on the resonance frequency, where you clearly see the increase of resonance frequency after installation of rock armor. But it's also being used in operational phase to evaluate the effect, for example, of storms on frequencies, where you can clearly see a drop during the storm and a recovery after the storm. Another parameter which has been very important over the last years, and several offshore testing and monitoring campaigns have been done to get a better understanding of it, is damping. So we've been analyzing damping within a wind turbine to see how it evolves in function of wind speed in the fore, aft, and side direction. But also very important is to compare the damping values of different structures. You clearly obviously see a big difference between jacket and monopile foundations in terms of damping. But what is more interesting is how to understand how the damping between turbines within an offshore wind farm differ. So this is all information that can be used towards design optimization and better understanding the dynamic behavior of offshore structures at site. Another aspect was then focusing on subsoil bending moments, where we're going to use optical strain gauges. Over the last years, we have instrumented several monopiles with optical strain gauges over the entire length, up below, going even below the seabed, to get a better understanding how those bending moments behave, so we can compare again as designed with as measured bending moments to assess the quality or improve the structural structure interaction models, such as the API or the currently used PISA standards. So as you understood, all this kind of in-field measurements are really focusing on improving the design of future wind farms. But what we see is that we are also now using it more and more also in a kind of a digital twin context, where we try to update models of each foundation within a wind farm in a monitoring context. And this is really part of some of the R&D projects, as Pieter-Jan mentioned, we are currently involved in. We have not been doing this alone for offshore foundations. As I said, we also looked at dynamic behavior of other structures, such as the jackup vessels. Here again, it was to really understand how, for example, the frequencies of surge modes and sway modes depend on the operational and environmental conditions, where by testing and monitoring, you can get an idea on how these frequencies again depend on, for example, jackup height or even how we see differences between the different locations the jackup vessel is installed. This again can be fed in better understanding of operating such a structure or improving design methodologies. A last example of why you can test and monitoring in the design phase is for design certification. This was the case for Van Oort for their slip joint foundation, where we actually have instrumented the slip joint with over 100 sensors, such as accelerometers, but mainly strain gauges to get an idea of the bending moments and hoop stresses you will have on such a foundation during installation and operation. The goal was supporting them for certification of this slip joint project. I think you have here a very nice illustration on how, for example, the hoop stresses on these foundations evolve at the moment that the slip joint is installed. So again, in-field testing is a necessity to support this kind of certification and design improvements. The other aspect that we had to highlight was how monitoring and testing also can be used for maybe root cause analysis. One of the cases we had was that we saw some failing components, for example, on offshore substation, and the root cause of this could mainly be found into the shocks and vibrations introduced by nearby equipment, such as diesel engines introducing vibrations, or his switching gear on an OWI-Lab introducing shocks. But also on wind turbines, vibrations have been excessive vibrations have been found and had to be investigated. Here again, we come to the fact that you can have vibrations due to natural causes, such as the effect of wakes on vibrations, or also rotor-induced vibrations, such as unwanted 1P rotor imbalance vibrations due to mass imbalance and aerodynamic imbalance, introducing vibrations in the first order mode and excessive loads on the foundation. But you can also have issues such as 6P rotor interaction, where there's an interaction with the second order structural mode, and as a result you get higher vibrations on the working platform, and this might result that employees complain about vibrations on this platform, or equipment that is installed on this platform is suffering from higher vibrations. And then the last two slides are the fact that, as I said, more and more we are launching monitoring and testing campaigns to have a better idea on how the loads in fields are compared with as designed, both for design optimization, but especially also for lifetime assessment purposes. So here we're really talking about the use of strain gauges, for example, to have an idea on how the bending moments of such an offshore foundation are evolving or changing into different environmental conditions. You can then also do rainflow counting and estimate fatigue parameters such as damage equivalent loads. Here again, the effect of how wakes affect the damage equivalent loads are clearly visible. But what is especially interesting is to very well understand how the loads on an offshore foundation depend on the different operating conditions, ranging from parked to run up to rated power to cutout conditions. This might be very useful information for an operator to see how, for example, park conditions for modern wind turbines in absence of aerodynamic damping can really result in higher load levels. So availabilities for modern wind turbines really become a lifetime driver. And so having a good idea on how they are in field is of course very valuable. And finally, we are using also today this load data actually to build data-driven digital twins, I would say, where based on the SCADA data and the interface loads and applying machine learning algorithms, you can use this in-field strain data to actually have an idea of the loads over the entire wind farm by only measuring at a subset of your foundations. So this is a very interesting evolution we are now seeing, and again shows what in-field testing and monitoring can bring you towards an operator of offshore structures. So thank you. This was the overview.
Thank you, Christophe, for also elaborating on the importance of field measurements compared to the other two colleagues who are already focusing on the laboratory experiments. There's a very good question actually in the chat box from Bart Peters. What is the physical phenomena that causes a drop in the resonance frequency during a storm and the recovery afterwards? Very good remark, Bart, that you have seen this. Christophe, can you elaborate on that question?
Yes, so it might be the result of a kind of a soil liquefaction happening due to the excessive loads during such a storm. And it's actually part of one of the R&D projects that we are involved now to really try to explain this drop in frequencies due to changing soil stiffness in the top layers.
Are there any other questions? Okay, it's well answered. So it's stressing the importance of understanding all the environmental constraints or boundary conditions as we have showcased in some of the slides. Is there any other question so far? No, then I will take over the screen and present the last presentation. So I will focus on the use of a large climate change in order to validate the effects of harsh environments. And what's it about? It's about this facility, which we have constructed 10 years ago in the port of Antwerp. It's one of the largest climatic test chambers, or we call it the climatic torch chamber, where we experiment, validate, and test large-scale electromechanical equipment for their functionality in extreme climatic conditions, ranging from -60 to +60 degrees. Thermal cycling can be tested there, humidity conditions, infrared heat, icing, you name it. So we want to recreate every extreme climatic condition on Earth to see how a machine is performing or what issues can occur during such operations. Again, the red line within this presentation is the environmental testing. Environmental testing is actually taking into account of looking into the natural environment or the induced environment, as Christophe already explained. In our case, this is focusing on the climatic effects, so the natural environment, like the effect of salt spray linked to corrosion, or temperature changes in the low and the high temperature and high humidities, but also, for example, freezing events, but also thermal shock if it's an induced environment, or high temperatures, as I will explain you later. It's all about checking the performance or specific performance losses, inefficiencies during such testings, the influence on the reliability or the lifetime of components. Will components fail due to certain environmental loads? And in some cases, for example, in respect to freezing and icing on wind turbine blades, it's also a safety concern in some applications. So what can we do in our laboratory in Antwerp? It's the red arrows that you can see here. Those are the conditions that we are currently focusing on within our roadmap. It's our goal to do all kinds of environmental tests over the coming years. So at this point, we cannot do them all, but quite a range already. With respect to turbines, there are cold climate turbine sites, hot climate turbine sites, and of course there are the nearshore and the offshore sites where high humidity and salinity is of importance. I will come back to that later. But to give you an example of induced environments, Christophe mentioned this in the mechanical environmental testing, for example, shocks and loads from other components that are causing an effect or a failure. Also, with respect to temperature or climatic conditions, this can be the case. To give you an example, if there is a hot summer and it's 35 degrees ambient temperature outside, and you have a turbine working in full load conditions, you also have an electrical load, which is of course influencing the heat production in certain components. So it means that in these cabinets or the modules within a tower, temperatures can increase up to 55 degrees or even more, which needs to be taken into account specifically for power electronics, for example, but also for cooling purposes or to determine what kind of coolings you need. And all these conditions need to be tested upfront or taken into account in the design when designing these components or these full turbines. Another example is then a cold start at minus 20 degrees, for example, when your transformer liquid is very viscous. This can lead to thermal shock phenomena and lead to certain issues or failures if it's not properly taken into account. So there, startup procedures are necessary to safeguard the lifetime of your equipment. Now, why do we do this? Wind turbines are currently either onshore and offshore installed everywhere on the world. It's a global market, and also, of course, more and more extreme sites are being chosen because the resources are quite favorable over there. For example, if you talk about wind energy in wintertime, the Scandinavian context and Canada, those regions are very good to harvest wind energy, of course. As in wintertime, also the air density is much higher than in summertime. But also offshore, as I explained to you before, and also hot climate sites